Good morning. We're going to start our very first lesson today, 1.1 power functions. So if you haven't done so already, please do the Minds On for lesson 1.1 in your Duotang. So today we are going to be able to recognize the similarities and differences between polynomial functions and power functions. You're going to be able to identify some characteristics of each of those, such as degree, symmetry, and end behavior. And by the end of the lesson, you'll understand the role of the leading coefficient in power and polynomial functions. Okay, so if you haven't finished the Minds On already, please pause this video right now, do it, and we'll talk about it in a sec. Thanks. Okay, so Minds On. It says, state the domain and range of y equals x squared. Well, y equals x squared is a power function. It's a very basic power function. You know it as a quadratic function because it has, of course, a degree of 2. That's the exponent. If I asked you to give me some characteristics of this, you would say, oh, it's a parabola, it opens up, it has 1, 0 at y equals 0 and x equals 0. It has one vertex at 0, 0. And you would also be able to state the domain and range. So we're going to state the domain and range like this for now in what we call set notation. So domain of any quadratic, x is an element of R. And I don't put the brackets. And the range would be y is an element of R with brackets such that y is greater than or equal to 0, right? This is a parabola that opens up, vertex at 0, 0, and so our range is everything above the x-axis. Okay, so that's our Minds On. Let's start the lesson. There's our learning goal. And so we talk about the definition of a power function. It's just the simplest type of polynomial function. So a power function is a type of polynomial function, but a polynomial function is not necessarily a power function. Just like a square is a type of rectangle, but a rectangle is not necessarily a square. Okay. So it has the form f of x equals ax to the n. So that just means that you can have a number in front of the x. You can have any whole number exponent here. So it can't be a half because that would be a square root function. It can't be -1. That would make it something completely different as well. It's just a nice whole number for n here. Okay, so some examples of power functions, y equals a because there's an invisible here. Let's see it. I'm not sure why that's not working. X to the 0 that I cannot write in here. This is x to the 1, x to the 2, x to the 3, etc. Okay? The exponent is the degree, so that invisible x to the 0 means the degree is 0. Degree 1, 2, 3, obviously 4 and 5. Okay, we give names to these particular types of functions. This is just a constant. If this is just a number here, that's a constant. Y equals x, y equals 2x, y equals -x. Those are all linear functions. Quadratic, of course, you know. And you're going to be learning cubic, quartic, and quintic this year. So what I want you to do right now is go to desmos.com on your phone, or you can go to use a graphing calculator, and I just want you to graph some of these power functions. And I want you to just observe a couple of things. So they look quite different. Y equals x is obviously a straight line that is on a 45-degree angle. Y equals x squared, you know, is a parabola that opens up. Y equals x cubed is something you don't know, and it should look something like this when you graph it. Y equals x to the 4th is going to look a lot like y equals x squared. Y equals x to the 5th is going to look like a lot like y equals x cubed, etc. Okay, so just have a little gander at that. Pause the video, graph a few, see if you can come up with some characteristics. All right, so now what we should have observed is that the graphs, the power functions with odd powers create graphs that go from quadrant 3 to quadrant 1. So when we're talking about quadrant numbers, hopefully you know how they're numbered. This is 1. It goes counterclockwise. 1, 2, 3, 4. Okay? So graphs that curve from quadrant 3 to quadrant 1 have odd power exponents. And the higher the exponent, the closer the curve gets to the y-axis. So this what might have been y equals x cubed here, and this should have been something like y equals x to the 5th. And of course, then the higher the exponent, odd exponent, the closer it's going to get to the y-axis. Even powers are graphs that make a U shape, so you already know that from y equals x squared, and the higher the exponent, the U shape gets closer to the y-axis. So if we had, for instance, if this was y equals, that's not very good, y equals x squared, then that should have been on the origin. Sorry guys, I'm just getting used to using this pen again. That would be something like y equals x to the 4th. Okay? So already you know some characteristics of polynomial functions just by graphing them. Okay, let's move on. I think that's the bottom of this page. Yep. Okay, so a polynomial expression is an expression of the form a n x to the n plus blah, blah, blah. That looks complicated, but all it means is that you might have something like this. Let's go 4x cubed minus 3x squared plus 1. That satisfies that criteria. You don't have to have all of the terms. You don't have to have exponents descending in order down. You can skip some. So you've got a coefficient here, plus or minus. You've got an x term. You've got a whole number exponent, and you can or cannot have a constant at the end. So here's an example, of course, of a polynomial expression. So this is not a power function, because a power function is one single monomial. Okay, it does not have more than one term. So what are the characteristics of a polynomial expression then? N is a whole number. We talked about that. X is just the variable. The coefficients are any real number, so it doesn't have to be a whole number. They can be, they can certainly be fractions or decimals or even symbols like pi. The degree of the expression is n. It's the highest exponent. So whereas we had the degree of a power function was just the single exponent because it was a single monomial, this one, the degree of this whole thing is just the degree of the highest exponent, or the highest exponent. The leading coefficient is the one attached to the term with the highest exponent. So in this case, the leading coefficient would be 4. And AO obviously is the term without a variable, and it's the constant term, so in this case it would be 1. All right. So a polynomial function is just a function, not an expression, so it's the same as what we were talking about above, but it has f of x equals. So let's look at some examples now. It says, determine which functions or polynomials justify your answer. State the degree and the leading coefficient of each polynomial function. So this one is not a polynomial function because this is a completely different function, the cosine function. So we'll say not a polynomial function, so we don't have to state the degree or anything like that. This is a power function, in fact. So it's a special type of polynomial function, and it has a degree of 4, and it has the leading coefficient is 3. Let's look at the next one. Does it satisfy the criteria? These are all whole numbers here. So I'm going to say this is a polynomial function. And its degree is 4, and its leading coefficient is 1. And the last one has a variable in the exponent, not a whole number, so this is not a polynomial function. Okay, so let's talk about some notation. Interval notation is a new way of expressing domain or range, and so it's used to express a set of numbers. It has intervals that are infinite, so we're going to use the infinity symbols. I know you've wanted to all along, and now in grade 12 you get to use those infinity symbols. This is positive infinity, this is negative infinity. We use square brackets to indicate when the end value is included, and we use round brackets to indicate the end value is not included. You'll see what I mean by that in a second. And a round bracket is used with the infinity symbol because we actually never get to infinity. So we're always trying to get there, so we use a round bracket. Okay. So those are some little hints about using interval notation, which is what you're going to use now, from now on, to express domain and range rather than set notation. So sets of real numbers may be expressed in a number of ways. So we're going to use what we call set notation or inequality notation. We can use interval notation, which you're going to learn, and we're going to use a number line, or we're going to express domain and range graphically as well. I'm just going to pause for a sec. Okay, so here what we want to do is express x is greater than -2 and x is less than or equal to 4 in each of these ways. So you're probably used to the inequality notation, which is part of set notation when we're using when we're asking you to express domain and range. So it's got the inequality symbol. So this says x. If you read from the middle and go left, x is greater than -2, and x is also less than or equal to 4. If we use interval notation, what we're saying is we're going from -2 to 4, but we're not including -2 because x is greater than -2, so it doesn't include -2. But then when we get to the 4, it does include the 4, square bracket. Okay? Much easier. And I'm going to be expecting you to use this interval notation from now on. And we can also express it graphically on a number line. So if you've got your number line, you know that at -2, x is not equal to -2. It's just greater than -2, so you express that with an open, unfilled in dot. And then you fill in everything because x is equal to all these values, and you fill in a big old dot here at 4 because x can equal 4. So what I want you to do right now is pause the video and fill in this chart to practice using interval notation and inequality notation and your number line notation here graphically. Okay? Thanks. Okay, sorry, I'm going to go back up and I'm just going to fill these in for you. So if I wanted to express x is between a and b but not equal to a or not equal to b, I'm just going to put a round bracket a, comma, b, round bracket, not including a or b. And if this one would be less, a is less than b, so I'm going to have a here. I'm going to have b to the right of it because it's greater than, and I would have open, doesn't look all that open, but I would have open circles here and here and a line in between. This one says x is between a and b but includes b and does not include a. So again, we would just have A is less than X, which is less than or equal to B. And over here, we would have our A and our B again. This is a little squished, I'm sorry. And we would include the B, but we would not include the A. And a nice thick line through there, right? And that's all because of the square bracket or the round bracket. If we have it the opposite way, that means that X does include A, but does not include B. And so I would have A here with a big old solid dot, and I would have B here with a big old round dot. This one, it includes both A and B, so square brackets around both, dot, dot, filled in between the two, and there we go. This one's tricky. It includes A, and it goes all the way up to infinity. Remember, this is the smaller value, so it's going to positive infinity, but it never includes infinity because we never get there, so it always has to be a round bracket around the infinities. So this would be saying, all right, what we're really saying is our X values are greater than or equal to A. So all you have to do is say X is greater than or equal to A. Remember, in inequality notation, we do not include the infinity sign. And then for this one, we would just put A here, filled in dot, and because it's greater than, we're going this way. Okay. X is less than or equal to A. Well, we would have that we're starting then at negative infinity, and we're going to A. We never have a square bracket around infinity or negative infinity, and it included A this time, so we have a square bracket because of the equal sign here. So X is less than or equal to A. We're going to have an A here. We're going to have less than or equal to, so whap, big old dot, and we're going to go all the way to negative infinity, which is left. X is greater than A. All right, so that would mean that we have A, and all our values for X are greater than that, so we're going all the way to infinity and beyond. And we do not include the A because X is greater than A. So again, we'll just put an A here. It doesn't include, so it's a big old open dot, and we're going to positive infinity. So, sorry. The pen's difficult to work with, sorry. Negative infinity to A means that all my X values are going to be less than A because we're going to negative infinity. And it doesn't include the A because of the round bracket. So again, A here, open, and we're going this way. Last one. Negative infinity to positive infinity is really just X is an element of R. It's everything. And we would just have a big old solid line here. Okay. Now let's talk about end behavior. So the behavior of the Y values is your end behavior, but it's as X approaches positive infinity or negative infinity. So in our particular class, we're going to express end behavior this way, by quadrants. So what we're really always talking about is how the function behaves as we move left to right on our Cartesian plane. Okay? Always sweep from left to right and ask yourself, what is happening to my Y's? Where are they coming from, and where are they going? They're always coming from one quadrant, even if it doesn't look like they are. For instance, if I had something like this, you can see that it looks like it's in quadrant 1, but because of the arrow, we would extend that beyond, and we would know that really it was coming from quadrant 3, and it was ending in quadrant 1. Okay? So always think about what is happening to the Y's, where are they coming from, where are they going, as you move from left to right. So describe the end behavior of a positively sloped linear function. Well, here, I just drew a positively sloped linear function. Can you describe the end behavior? You're going to be going from quadrant 3 always. It has to end in quadrant 3. And it's going to go to quadrant 1. And describe the end behavior of this function. Well, I know this is a quadratic function. I know that it's been shifted up 4 and that it opens down. So I get a little visual in my mind before I describe the end behavior. So I see my arrows here. I can see that because this was opening downward because of the negative here, that I am going to go from quadrant 3 again. So again, we're going left to right. So this is going to end in quadrant 3. It's not going to turn and go to another quadrant. And then we're going to go on to quadrant 4. Okay, I'm going to pause this now because we are into period 2. Okay, we're going to talk about another characteristic of power and polynomial functions, and that is the idea of line symmetry. So line symmetry exists if there's a line such as an axis of symmetry for a quadratic. So it's a line that cuts the function in half and creates symmetry. Okay, so it divides the graph or the function into 2 equal parts. In this particular example, you can see that this is a parabola. The vertex is at 2, 0, and you can see that the axis of symmetry is at x equals 2. So there is line symmetry for this parabola at x equals 2. Point symmetry is another notion that you're going to use to identify certain power and polynomial functions. And point symmetry exists, this is kind of a little bit different, if you can take a particular point on a graph and rotate the graph through 180 degrees. So 180 degrees, so around, that's half a circle, right? Around to this quadrant here, if we rotated this, we would end up with the graph back. Right? This part would become this part, and this part would become this part if we rotated it through this particular point, through the origin. So it is said that point symmetry exists or about the point 0, 0 or about the origin. Okay, so we're always rotating 180 degrees to determine whether point symmetry exists. Okay, so let's practice. It says draw a function on the grid for which point symmetry exists at the point 3, 2. So the easiest way to do that would be to go to the point 3, 2, draw in a little point, and then reproduce the graph that's here. We know that if we, let's see if we have something-ish like that, a little angled there. If we rotate this through 180 degrees, we're going to exactly have that graph back if we're rotating it around the point 3, 2. We could have also had a line through the, let's see, through this point, this point, this point, and a straight line. And if we had rotated it through 180 degrees, we would get our line back. Okay, so that's point symmetry. Okay, so let's do some examples. So for each of these, I want you to state the domain and range in all 3 ways now for each of these functions. I want you to describe the end behavior and identify any symmetry. So let's look at the first one. Well, this one looks like a cubic or an odd degree function. There are arrows at if the graph goes to the end of the grid, then it's considered that it goes on forever, even though there are no arrows there, they're implied. So in the domain for this one is x as an element of R, and the range is y as an element of R. So I'm just going to put x is an element of R, y is an element of R for this. That's in inequality notation. In interval notation, we would have round brackets, negative infinity to positive infinity round bracket for both x and y. So we can put x as an element of and y is an element of negative infinity to infinity. Not a lot of room here, sorry about that. So that's the domain and range. And then that's in interval notation. And then in line notation, it would just be, maybe if we switch colors, we could just go like this and just indicate this is the x and the y. Okay? Now for the, sorry, I just want to double check again what we were doing here. End behavior. Well, we can see as we move left to right, what is happening to, as we move left to right, we can see that this is, this was approaching the negative infinity, and as we move this way, this is the y's are approaching positive infinity. So it's coming from down here, it's coming from quadrant 3, and it's going to quadrant 1. So sometimes we think about end behaviors as what's happening to the y's as the x's are approaching negative infinity and positive infinity. So what's happening to our y's as they approach, as x approaches negative infinity, the y's are approaching negative infinity, which is in quadrant 3. And as our x's are approaching infinity this way, positive infinity, our y's are approaching positive infinity, and that's going to end in quadrant 1. Okay, so we always express it this way, quadrant 3 to quadrant 1. Okay, and then any symmetry existing, and we can see that there is point symmetry. I'm not sure why that looks like it's not going to work. So point symmetry, this is 3. And you have to say where, which point, and so I'm going to say about, you could say about the origin, or you could say about the point 0, 0. Okay, let's look at the next one. So the domain for this one is x as an element of R. So again, we can just put x as an element of R. The range, however, is not. The range is going to be set bracket y is an element of R such that y is greater than or equal to 0, close bracket. We've got that in interval notation. We would write that, of course, the domain would be x as an element of negative infinity to infinity. Oops. And the range, where's my pen? Sorry, I'm having some difficulty with my, just bear with me for 2 seconds. Let's see if I can get this going again. Okay. And the range, come on little pen, is y is an element of square bracket 0. We need to include the 0 all the way up to infinity, which of course we don't include. Okay, and then if we wanted to do it with a number line, the domain would be that solid line again, and the range would not be a solid line, it would just be from 0 all the way up. We would include the 0 though, so we'll put a 0 here. We're going to put a big old solid dot. Oopsie, I should maybe do that in red. Solid dot going this way, all the way to the arrow. And is there any symmetry? I'm going to say yes, there's symmetry. There's line symmetry. About x equals 0. So always say which line the graph is symmetrical in, and in this case it's the y-axis, which is of course x equals 0. Okay, I don't think there's another one here to do. Okay, so the domain and range in inequality notation is the same. X is an element of R, Y is an element of R. If we were doing that, it would be X and Y are an element of negative infinity to infinity, round brackets. If we were doing it on a number line, we would just draw the number line and, of course, include that whole line. Okay. What about the end behaviors? Oh, did I do the end behaviors for the previous one? Just going to jump back. I think I skipped it. So let's go back and put in 2. The end behaviors for this particular graph, this parabola, we can see that it goes on forever, approaching y is infinity, up in quadrant 2, and then it goes and ends in quadrant 1 if you go left to right. So you're always going to say left to right, which is quadrant 2 to quadrant 1. Sorry about that. All right, let's go back to our negatively sloped line here. And the end behaviors for this then, it's going to end in quadrant 2. And so it's sort of ending over there in quadrant 2 and ending over here in quadrant 4. What are the symmetry for this one? For sure there's point symmetry. Go back to black. So this is point symmetry. Like say which point? About 0, 0. And there is actually line symmetry as well. This one's harder to see. About the line y equals x. So for instance, if we took this point here, this was the point negative 1, 1. Remember, y equals x means that you're just going to switch your x's and your y's, and so then on that would become 1, negative 1, which is down here, right? So if we, the line y equals x is kind of here. If we reflect in that line, we get our line back. Okay, but that one's difficult to see, I get that. So now what we're going to do is we're going to sort of match these equations to their end behaviors. So let's just summarize for a second. I'm going to summarize hopefully what you've learned about odd and even degree functions. I'm just going to draw 1, 2, 3, 4 little grids. And if I drew something like this, you should be able to tell me whether that's even or odd degree now. So this is an odd degree, and the leading coefficient is positive. Okay, we know that if I graphed y equals x cubed, it's going to look like that, which means my leading coefficient was positive. If I reflect that, if I graphed y equals negative x cubed, that's going to be a reflection in the x-axis, which is going to give me that graph. And so I know that that is an odd degree with leading coefficient negative. Let's go back to our handy-dandy parabola. We know that's an even degree function. And even degree functions look a lot alike. And that, of course, has a positive leading coefficient because it opens up. We're going to have one that opens down. If we have something like that, we know that that is even degree. And the leading coefficient is negative. With that in mind, let's, fill in this chart. Oopsie. I lost somehow. I believe we're back. Okay. So, which one of these graphs below extends from quadrant 3 to quadrant 1? Only one of them, right? So it's only the odd degree functions that have a leading coefficient that's positive. So odd degree, we'll look in our options with a leading coefficient that's positive. That's out, that's out. There we go. Y equals x to the 7th. And y equals 2x, because that's got that invisible exponent of 1. Why are those the ones? Because they're odd degree with a leading coefficient positive. How about extends from quadrant 2 to quadrant 4? So let's look. Which ones extend from quadrant 2 to quadrant 4? We can see that that's the second case. Odd degree, leading coefficient negative. So we go back to our choices here. We can see that that would be y equals negative 2/5 x to the 9th and y equals negative 4x to the 5th. Y, odd degree, leading coefficient negative. Okay, if we extend from quadrant 2 to quadrant 1, then we look at this one, 2 to 1. So that is even degree, leading coefficient positive, even degree, leading coefficient positive. So I've got y equals 5x to the 6th, and that one's out. I've got also y equals x to the 10th. So if you graphed both of those, they would have that in behavior, quadrant 2 to quadrant 1. These are both even degree, and they are leading coefficient positive. Last but not least, if your graph extends from quadrant 3 to quadrant 4, it's got to be an even degree with a leading coefficient that's negative. And so what are our options here? That would be y equals negative 3x squared for sure, and y equals minus 0.5x to the 8th. That is even degree, leading coefficient negative. Negative. Okay, that is all for today. Thanks for listening, and please do your consolidate if you haven't already done it. And there is homework associated with 1.1. Thanks a lot. Bye-bye.